Welcome to this section of statistics. The following content is brought to you by Texas Instruments. Find a local Texas Instruments near you today. All right, let's get started. I'm Mr. Brandrick. You know me, I know you. Not really. Let's get started with Chapter 9. Now, Chapter 9 continues the stuff that we were talking about the last 2 weeks, but we're going to just learn more about what to do when things go wrong. Okay? So let's think about what we've been talking about with linear regression. What's the first thing you should do when you are doing a linear regression?
Identify.
Well, even before I can do the three things, I need to make something. A scatter plot. I need to make a scatter plot. And then, Roberto, I can talk about the direction, form, and strength in context. Once I decide that it has a linear form, then I can run a linear regression. And that's where I write the equation with our little hat. Okay? Remember back to last week? Yeah, Marcel's like, yeah, I remember that. All right, yeah, absolutely. Now, once we do the regression, we have to check something to see if it's appropriate. What do we check to see if it's appropriate? Not outliers. The residuals plot, Roberto, very good. We must check the residuals plot to see if there's no pattern, and if there's no pattern, then we're okay to use that model. Okay? So this chapter is going to begin to talk about what to do when things don't happen perfectly nice how we had last week. Okay? So let's take a look at a couple of things here. Again, as we've talked about in this class, if it's up here and not on your notes, please make sure you're writing it in for that 5 out of 5. Okay? Now, all this stuff hopefully makes sense to you. When you're looking at the scatter plots, I want to direct your attention to the scatter plots. And man, I love penguins. They're the best. All right? When you look at the one in red, that is the scatter plot. They think that the duration of a dive for emperor penguins explains their heart rates during that dive. I'll repeat that. They're telling you that the length of how long that penguin is underwater explains how fast their heart beats and pumps blood. Kind of makes sense to me? Fair enough. Okay. How would you describe the form of the one in red? I'll move it up a little bit. How would you describe the form in red? See, it looks like it's linear with a little bit of a negative, but do you see this bend here? Some people pick it up in the red one, some people don't. But take a look at the residuals plot when they do the residuals. Do you see that bend is even more pronounced there?
Yes.
All right, so sometimes you might do all this whole thing, and you might not see it till you get to the residuals. You're like, oh, I can't use this model. It's not appropriate. Okay? So that's what this is about. If curved relationships are showing up at some point in the process. All right, let's keep going. All right, now, sometimes what will happen is that you'll actually end up finding that you have groups of data that you should separate. That's going to happen to us today with our first example. We're going to do an example today looking at, I believe, graduation numbers by year. And we're going to see that there's actually different groups that we should take apart and look at them separately. All right? And this might happen in the scatter plot. It might happen in the residuals plot. But we're always looking and keep being aware of the fact that we might have groups that we should take data out and look at it individually. Now, this next word, extrapolation. This is where you're going to get into trouble. And as a society, we love to do this. The idea with extrapolation is that what's happening presently, you think is going to continue into the future forever. Okay? So that's what we do as humans. We think whatever is happening right now, we think is going to continue just like that forever. And as you know, you've been alive for 16, 17, 18 years. You know that's not true. Okay? Yes. Marcus back. All right. So whenever you're venturing out further in the X direction than what you have for your data values, you will be running into that issue of extrapolation. I'm not saying you can't use your model. But if I look at you using your model and you're using extrapolation, I'm going to be worried about what you're predicting. Okay? That's the whole thing about when we look at our world, we're trying to predict what happens in the future, and do we know what's going to happen? No. We don't. That's the hardest thing to predict. You can absolutely guess, but you should always be cautious about that guess because things change. Roberta. Yes, absolutely. I think I told you guys this. I read a book that was all about analyzing with the meteorology and all that stuff, and it was saying that you shouldn't actually look at any weather reports until 36 hours before it matters, because everything else is not important. Like, do I look at like the week ahead of what it thinks it's going to happen? Absolutely. But speaking of this weekend, it said it was going to rain from like 2 a.m. to 8 a.m. at my house. 85% chance of rain. No rain. All right. So that's why I deleted the app. All right. Let's look at the next slide. Now, these three words can get a little confusing. These three words, and really the last two, are kind of what gets students a little confused. You guys have heard outliers in this word for a long time, so you're always on the lookout for an outlier, like this red point. And what I love about this scatter plot and linear model example is it shows you how influential these outliers can be. Do you see how this red point changes your line, your linear model? It is changing not only the intercept, but also the slope. Any point that changes your linear regression model is influential. I'll say that again. Any point that changes your linear model is influential. Everybody okay with that definition? Okay? So we always, if we think we have an outlier, we always want to run everything with it included and also without it included to see if there's a big difference. If there's a big difference, then we should report both. If there is not much of a difference, we can leave it in. Like run both models, like one with it in, one with it out, and compare them. Because again, the way I view it, George, is like you're doing all this work for someone to read, and it's up to them to decide what they want to do. We can make our own decisions, but we want to make sure they have all the information that they can make their own decision. All right? Excellent. Now, let's talk about looking at another example here at the bottom. Do you guys see where it has shoe size and IQ? If you just change the IQ to be a very smart person or a not so smart person, you can see what happens with the model. It changes the slope from a positive to a negative slope. That's obviously in a very extreme case. And you guys see how the X value is way out here, probably near around 30. See how it's out here? Any value that has an X that's far away from all the other X values is said to have leverage. So that's this word leverage. All right. So I'll repeat that. Any data value that has an X that's far away from all the other X's is said to have leverage. Now, the question I usually get from students is, can you have points that are both have leverage and are influential? What would you say about these red X's? Yes, because those X values are really far away from all the other blue dot X values. And what's it doing to the linear model? It's changing it, right? One time is positive, one time is negative. So for this one, you would say it has leverage and it's influential. But there might be times, guys, where you look at an X value that's really far away, so it has leverage, but it doesn't really change the model much. So the hard part about it is sometimes these influential points, because they pull the line towards it, have small residuals. Okay, so you might not see them in the residuals plot affecting much. So that's what they can kind of hide in the residuals, is what I'm saying. Okay. All right. Almost there. Now, we've talked about this a few times, but just because you decide that there's a correlation between two variables does not mean that there's a cause and effect relationship. And remember how we talked about R squared last week? R squared is a measure of how good a model is at modeling that linear relationship. The closer it is to 100, the better you feel about using it. But even if it's like 98% for your R squared, you still should not go as far as saying cause and effect. So always avoid this idea of causation. And you guys remember the example that I mentioned about the number of TVs and the life expectancy. Okay? There's a perfect example. It's in your textbook in Chapter 9 about that. Any questions so far? Yeah, Jessica. Who can explain what leverage is to Jessica? If a point has leverage, what are we saying about that point? Very good. Its x value is far away from all the other x values of the other data points. Okay? If it's influential, then it changes considerably the slope of your line. All right. Yeah, George. Most of the time, George, points that have leverage and are influential are also outliers. Yeah, but sometimes it might be 2 or 1. So just because it's all 3 on one example doesn't mean it's always going to be like that. Say it again, Roberto. It is complicated.
No.
It is. It can be confusing. You're like, wait, I thought, yeah, I mean, it's hard. Again, how long have I been doing this? Over a decade. Okay? Over a decade. This portion brought to you by dentures. All right. Working with summary values. The last slide. Okay? There will be times where you're out in the world, maybe your job or just reading something, and you might be looking at some information like we're teaching you right now, and it might be summary statistics, like the average. So the example I like to look at is this one down here. Do you guys see the scatter plot on the left? You guys see the one on the left? Okay. Then you see the one on the right? Do you see how the one on the right looks stronger? Like it's tighter? All right. This is individual heights of men explaining their weight. This is average heights of men explaining their average weight. Do you see how the averages are much stronger and tighter? Okay, that's true of summary statistics. It will make you think that the relationship is stronger than it really is. And the downside is once somebody gives you summary statistics without the data values, you can't undo it. You can't somehow magically say, oh, well, I've got the mean, so I want to go back to the individual data values. You have to actually find the individual data values. Okay, so just be cautious of that, and not just like for our class, but in life. If you're reading something and they're trying to sneak in there that it's like averages, they're trying to make you think it's stronger than it really is. Okay? You're good. We're going to do it again. The idea is that if you look at individual data values and their relationship on a scatter plot, and then you look at averages. So let's say I look at the individual data values for all my freshmen at this school for something, where I'm looking at, yeah, but what's another quantitative value I could use? Their grade in their math versus their grade in their science class. How about that? Okay? And then I decide, instead of doing all 150 freshmen, I decide to do averages based on, that could be interesting, but based on the school they went to for grade school. So I've got average data values. Maybe I've got, how many schools do you think feed into this one? 20? 15? I don't know. So now I've got, instead of 150 data points, I've got 20. And those 20 are going to look much tighter as opposed to all 150. It'll be more scattered because those are summaries. Those are averages. Man, nice job, me. That's awesome. Way to go. Way to go. I felt pretty good. I just pulled it out of nowhere, guys. I mean, like, come on. Give it up. There we go. All right. Tune in next time.